Good afternoon. My name is Hongyao. I just graduated from Harvard. This is joint work with Fang, who is now at CMU, and my advisor, David Parks. So I'm going to talk about pricing and dispatching in ride-sharing platforms such as Uber and Lyft. And the goal is to provide efficient and reliable transportation for the riders without the power to tell the drivers what to do. Let me start with two important features of ride-sharing platforms. So the traditional taxi systems have fixed prices. So the prices are very reliable, but the service is very unreliable. There's no guarantee on how long you'll have to wait for a taxi, or even if you can get one at all. But the ride-sharing platforms emphasize reliability. And for example, Uber used to state its mission as transportation as reliable as running water, everywhere for everyone. And when demand exceeds supply, these ride-sharing platforms use dynamic surge price to guarantee that there will be a car within several minutes wait, as long as you're able to pay the price. The other interesting feature is that, and also more generally for the ride-sharing economy, is that both sides of the market, the riders and drivers, are customers of the platform. And the real-time flexibility for the drivers to drive wherever and however they want is the most important reason that the drivers drive for these ride-sharing platforms. For example, Uber advertises itself to drivers as work that puts you first, drive when you want, and earn what you need. And for everyone in the room, it's not surprising that when we put together dynamic surge pricing and also autonomous and self-interested drivers, very interesting things happen. I first heard about this from a talk at EC actually in 2016 when Keith Chen talked about market design at Uber. So this is a screenshot of a very early Uber drivers app. We can see that space is divided into these large areas. And here 2.1x means that a trip with an origin in this area is going to charge the rider and pay the driver 2.1 times the surge price. So what happens is that as soon as the drivers see the surge heat map like this, there's a vacuum of drivers on the 2.1 side of the boundary because everyone had turned off their phone and tried to drive to the 5x area as fast as they possibly can because they want to make 5x, they don't want to make 2.1x. So the result of this is that for a rider at the 2.1 side of the boundary, even if she's willing to pay 5x the price, there's no driver that's willing to pick her up. So this hurts the reliability and welfare of the platform. So we started thinking about this, but it didn't become a research project until roughly 2 months later when we read in the news that drivers strategized at TD Garden in Boston, which is our stadium for hockey and basketball. So basically what was happening was that 10 minutes before the end of a sports event, the drivers will all drive to the stadium and they park there and they turn off their phones. So why do they do that? They don't want to be sent away 10 minutes before the game ends at a low price because they know that the price is for sure going to surge. So this is the moment we realize that this is actually the mechanism's problem. It's not the drivers because it's inefficient to send the drivers away 10 minutes before the game ends, and the drivers are just best responding to the prices. So let's look at an example to see how these market failures can happen. Here is a toy economy modeling 3 time periods around the end of a sports event. So I have time running from 9:50 p.m., which is time 0, all the way to 10:20, which is time 3. And each node is a location time pair. We have 3 locations, A, B, and C. And the sports event is ending at time 10 p.m. at location C. And we have 3 drivers. Drivers 1 and 2 are able to drive starting in location C at 9:50. And driver 3 is able to drive starting at B at 9:50. And the edges in this graph represent rider trips. So here we have 2 riders, riders 1 and 2. They hope to get a trip from location C to location B starting from 9:50. And each rider 1 is willing to pay $10 for the trip, and rider 2 is willing to pay $20 for the trip. And from location B, we have 2 riders. One of them hoping to go to C, willing to pay 10, and the other hoping to go to A, willing to pay 20. And when the game ends at location C at 10 p.m., we have 4 riders hoping to get trips there, and they're willing to pay a lot of money. And we also allow trips within the same location. So here's a rider requesting a trip from B to B. So Now let's think about what will happen if we just naively clear the market for each location and time without thinking about the future. So we call this myopic pricing. Let's color code the drivers. What happens at 950 is that for location C, we have 2 drivers and 2 riders. So we'll send these 2 drivers to pick up these riders and go to B. And the set of all market clearing prices anywhere between 0 to 10, and if we set the lowest market clearing price, this trip is going to be priced at 0. So here, for simplicity, I didn't introduce any trip cost. So think about this 0 as this price is just covering the driver's cost. And our reformer model is able to consider driver costs. And then for driver 3, the driver 3 is going to be sent to location A because rider 4 is willing to pay $20, which is higher than rider 3 willing to pay 10, and this trip, if we set the lowest market clearing price, is going to be 10. And then 10 p.m. arrives, one of the drivers pick up this rider. Again, this trip price is set to be 0. And then no driver is at location 1 at 10 p.m. So we have to set the price to be at least 100. And here is the outcome under myopic pricing if all of the drivers follow the platform's dispatch. First, we can see that the social welfare, which is defined as the total rider value minus the driver cost, is only 60. So it's apparently leaving a lot of welfare on the table. And the second problem is that the prices coming out of this mechanism, it's very unsmooth in both space and time. And if I were driver 1, by the end of the day, I made $0. But if I look at this price jump from 0 to 100, then I would just stay in location C for one period of time and then pick up one of those wealthy riders, and I can be paid a lot of money. And the third problem is externality. Like a trip brings me to the destination of the trip, and if I were driver 3, I was strictly hoping to go to location C instead of location 1. So in this paper, we study how to provide reliable and efficient transportation while still leaving the drivers with the flexibility to decide how to work. Our main result is a mechanism which is robust. It responds to the driver's deviation from the dispatches, yet it's still able to guarantee incentive compatibility in the sense that the drivers are always willing to accept the dispatches that they receive from the platform. We have a very simple model, but it's rich enough to capture spatial imbalance and temporal variation of demand and supply, which is what's driving many of these problems. So here's our model. At each time, the timeline of a mechanism is like this. The mechanism will dispatch the available drivers to either pick up a rider or to relocate to some location. And it will also specify the payment for each rider and driver. And then the drivers can decide whether to accept the dispatch or to decline the dispatch, in which case they can stay where they are or relocate to any location they would like to go. And then the mechanism would pay only the drivers who had followed the platform's dispatch and charge the riders who are actually picked up. So we can see that the mechanism we consider do not penalize drivers for not following the dispatch. And here's how we model supply and demand. We have a discrete time finite planning horizon model where time runs from time 0 all the way to time capital T, which is the length of the planning horizon. And then there is a set of discrete locations. The distance between any pair of locations models the number of time period it needs to travel from the origin to the destination. And for every driver, if the driver completed trip starting from location A, ending in location B at time at time T, then this driver incurs a cost of CABT. And then we have a set of drivers. Each driver is able to drive for the platform starting at some location at some time. So we assume that the drivers will all remain the platform until the end of the planning horizon, and that the drivers don't have idiosyncratic preferences over riders or locations. And the drivers are strategic. They would like to optimize their total payoff, which is the total payment they collect minus the total cost they incur. And we have a set of riders. Each rider hopes to get a trip from some origin to some destination starting at some time. And then the value of a rider models the willingness to pay of the rider for the trip. And we assume that the riders are impatient, meaning that the riders are not willing to walk, and they're not willing to wait until one period after their requested time. And then the riders are price taking, meaning that they would like to have a trip as long as the price for the trip is not higher than their willingness to pay. And finally, you assume that the supply and demand over the entire planning horizon is known to the platform and to all the drivers. It is also sufficient if the drivers have the common knowledge that the platform has the correct information. So we can see that the focus here is on agency. So we would like to price the trips properly with respect to each other so that the drivers are always willing to accept. So the focus is not to incentivize the participants to truthfully report this information to the mechanism. Okay, so given this model, the first question to ask is that if we assume all of the drivers will always accept the dispatches, what would be the outcome that we would like to see? So here's the welfare optimal planning problem. A plan describes everything that happens over a planning horizon. For riders, it describes whether or not a rider is picked up. For drivers, it specifies the path the driver takes in space and time. And this can include both rider trips and relocation trips. And a plan also describes the payment for each rider and each driver at every time point. And we can show that the optimal dispatching problem can be written as an integer linear program with an exponential number of decision variables. But we show that this problem can be reduced to a minimum cost flow problem under our model. And then total unit modularity holds, so the LP relaxation has an integral optimal solution. So with integrality, we can decompose the optimal flow into paths for individual drivers. So this would be the welfare optimal plan for the example that we were talking about just now. We can see that all of the drivers, they either stay in location C or they drive to location C and then pick up these high willingness to pay riders, and then we can achieve optimal total welfare of 300. And the integrality not only allows us to compute this welfare optimal outcome, it also allows us to derive origin destination time-based anonymous trip prices from the dual. So these numbers in italics is a set of competitive equilibrium prices. So in this context, competitive equilibrium requires that for each rider, if the rider is picked up, then the rider is willing to pay the price for the trip. And if the rider is not picked up, then this rider does not strictly prefer to be picked up given the price of the trip. And for drivers, it requires that each driver is assigned a path in space and time that has a total payoff that's the highest among all of the feasible paths of this driver. So here we can see that all of the paths that's feasible for drivers 1 and 2, they wouldn't give these drivers a payoff that's higher than 80, which is what they're getting. So more formally, we show the welfare theorem that a plan is welfare optimal if and only if it can be supported by a set of origin destination-based anonymous CE prices. And we show core equivalence, meaning that any CE plan is in the core. So an outcome is in the core means that there cannot be a coalition of riders and drivers. They break out of the mechanism, make a plan among themselves, and they're happier. So any CE plans in the core, and any core outcome can be supported by a set of CE prices. And we also show a lattice structure of the driver's total payoff in all the CE outcomes. So there is a driver optimal outcome and the driver passimal outcome, which is paying the drivers the smallest amount that they can get paid in any CE plan. So here, what I was showing is the driver passimal CE plan. In the driver passimal CE plan, from any location, any time onward, each driver is paid how much the society gains if we replicate this driver at that time, at that location. So as an example, for driver 3, who is at location C at 10 p.m., if we replicate this driver, the replica driver is going to be asked to pick up rider 9, who's willing to pay 80. So as a result, the continuation payoff for driver 3 from time 1 onward is 80. So given all of these, it's already looking promising. We can show that under our model, a CE plan always exists. And the prices are smooth, and it even deals with the continuation problem properly. But what it does not answer is what happens when a driver did not follow the dispatch. So for example, if driver 3, instead of going to location C, the driver stayed in location B for 1 period, if we don't update the plan, then at least 2 things can go wrong. First, rider 6, who's willing to pay 100, looking at the price of 80, say, oh, please send me a car. But now driver 3 is no longer able to pick up rider 6. And the other problem is that driver 2 is asked to pick up someone who's willing to pay 90. So for driver 2 who is at C, if we send driver 2 to pick up rider 6, we actually improve welfare. But if we don't update the plan, then we cannot do that. So how do we update the plan? We show that if we just naively update the downstream plan at every time, it doesn't work. So the mechanism we design only updates the plan after some driver have deviated. But now we need to deal with the strategic reasoning that, what if I can deviate from a plan and trigger replanning downstream, and maybe I can get paid more money. So this is our result. We propose the mechanism, which we call spatial-temporal pricing mechanism. The mechanism is very simple. At the beginning of the planning horizon, this mechanism computes a driver pass mode CE plan and then starts to dispatch the drivers to trips accordingly. And at any time t, if there is a deviation in the previous time period, then the mechanism would just take the state of the system at that time and then just recompute a driver pass mode CE plan and then start to dispatch accordingly. So you can see that the mechanism is robust and it does not penalize drivers. So it's aligned with the flexible spirit of the sharing economy. And then we can show that the mechanism actually is subgain perfect incentive compatible, meaning that if everyone else always follows the platform's dispatch, then it is also to my best interest to follow the platform's dispatch. And then we can show that in equilibrium from any history onward, the outcome is welfare optimal. It's envy-free, meaning that no rider who's requesting the same trip envy each other, and no driver who's ever at the same location and time together envy each other's continuation payoff. And the outcome is also course selecting. So very briefly, let me sketch the proof intuition. So the mechanism induces an extensive form game among the drivers. And the strategy of each driver at each history is to decide whether to accept the dispatch or to do something else. And then we can use the single deviation principle. So the only thing that we need to show is that there isn't a deviation of 1 step that's helpful. And then to show that, we make use of 2 facts. One, the first fact is that the continuation payoff of each driver from any location and time onward is equal to the unit replica welfare gain. So how much society gains from an extra driver like that. And we make use of the M natural concavity of the objective of the mean cost flow problem. So this basically means that there is stronger substitution between drivers at the same location and time in comparison to drivers who are at different locations and times. So this is the intuition of the proof. I'm running out of time. In the paper, we also have some discussion on why dynamic VCG doesn't work and the impossibility result on dominant strategy. So subgain perfect is the best that we can hope for. And then we have a bunch of simulation results. And let me leave the future steps here. So we're quite interested in understanding how to incorporate a stochastic model for demand and supply and also do some empirical study. So thank you very much.